Let's solve the first problem from the Physics 151 Spring 2025 second midterm exam. So that problem starts with this capacitor question. We have two capacitors in series, C1 and C2, and they are wired to a 12-volt battery, and we want to find the charge on each capacitor. So ordinarily, two capacitors in series have the same charge. So this would be like, so here's the plus side of the battery, so this would be plus Q, minus Q, plus Q, minus Q for the same Q value. This is true if these capacitors start out uncharged and then are charged up by this battery, or charged up by any mechanism that leaves these two capacitors just in series on the same branch of a circuit. That's almost always the case for capacitors in series. There are some really weird cases where that's not true. For example, we saw this problem at some point from an old midterm exam. This was from the spring 2018 second midterm exam in Physics 151. And in this case, battery is connected between A and B, and everything works out in the expected way when the switch is open. So these two upper capacitors are in series, they have the same charge as one another. These two lower capacitors are in series, they have the same charge as one another. And then this switch is closed. And when the switch is closed, now charge is able to move kind of to this midpoint. And normally for capacitors in series, this midpoint has no net charge because you've got, say, minus Q here and plus Q over here for the same value of Q. Just as this midpoint here has no net charge because you have minus Q here and plus Q here. So this particular problem is a really strange problem where we've kind of snuck some non-zero charge into this midpoint between two capacitors. So I think in this problem, this is kind of a digression, but I think in this problem from spring 2018, if you close the switch, which allows some charge to move here, and then you reopen the switch afterwards, you would wind up with a solution in which these two capacitors are in series with one another, but they do not have the same charge on them. Okay, but that's a really unusual situation. So let's end that digression. So in all ordinary cases, capacitors in series have the same charge. So we can actually use the loop rule here. We can just make a little loop like that starting from the top of the battery. So we can say battery EMF minus, so here you have to be aware of which side of this capacitor you expect to be plus and which you expect to be minus. And you can kind of treat the capacitor as if it were a little battery for the loop rule. So here's minus, so for a capacitor, Q equals CB. So the voltage across a capacitor is Q over C. Okay, so this is minus Q1 over C1 minus Q2 over C2 equals 0, but because they're in series, Q1 equals Q2 equals, let's just call it Q. So I can erase the subscript 1 and 2 from the charge here. EMF equals Q times 1 over C1 plus 1 over C2. And then I can solve that for Q. Q equals the battery EMF times 1 over C1 plus 1 over C2 reciprocal of. So that is Q equals this equivalent capacitance times the voltage, the battery EMF. And this equivalent capacitance makes sense for two capacitors in series. Two capacitors in series combine the same way as two resistors in parallel. So this is 1 over C1 plus 1 over C2. And for two capacitors, you can say that's the same thing as C1, C2 over C1 plus C2. That's a little quicker to evaluate. That is 6.67 microfarads. So 6.67 microfarads times 12 volts. So that's easier to work out if we leave this as 20 divided by 3. So the equivalent capacitance is 20 over 3 microfarads. So then the charge is 20 over 3 microfarads times 12 volts. Q equals C V. So 12 over 3 is 4. 4 times 20 is 80. So Q equals 80 microcoulombs. So this is 80 to 3 significant figures, 80.0 microcoulombs. So that was part A. For part B of this problem, we insert, with the battery connected, a dielectric with dielectric constant kappa equals 2 into capacitor 2. So between the two plates of capacitor 2. Well, we have to figure out what that does to capacitance C2. So C2 was 20 microfarads. So we have now C2 goes to kappa times this original 20 microfarads. So that is 40 microfarads. So now we have C2 is 40, really 40.0 with our three significant figure convention. C2 is 40 microfarads now. Otherwise, the problem is unchanged from before, so we just need to update the numbers. So now we have 10 microfarads in series with 40 microfarads. That answer will be 40 divided by 5 is 8. 40 times 10 is 400, divided by 40 plus 10 is 50. 400 divided by 50 is 40 divided by 5 is 8. So this is 8.00 microfarads with our course's three significant figure convention. 8 microfarads times 12 volts is 96.0 microcoulombs. Now for part C of this problem, we first disconnect the battery. So the battery was connected and left charge plus Q, minus Q, plus Q, minus Q here. And using these capacitor values, 10 microfarads the top capacitor, 40 microfarads the bottom capacitor with the dielectric inserted, we worked out that this charge Q was 96 microcoulombs. Now we're going to disconnect the battery like that. So once you disconnect the battery, this charge can't go anywhere. So this plus Q can't go somewhere else. This minus Q can't go somewhere else. And this net charge of 0 here, minus Q here, plus Q here, can't go anywhere else. So now with this, in this state, we remove the dielectric. So we're going to pull out this dielectric. It's not there anymore. And that means we're now back to C2 equals 20 microfarads. So now we know the charge on each capacitor, and what we're asked to provide is the voltage across each capacitor. So just to be completely unambiguous, I'll label this point A, and I'll label this point B, and I'll label this point C. So V1 equals Q1 over C1, which is just Q over C1, which is the same 96 microcoulombs divided by 10 microfarads equals 9.6 volts. And by the way, the voltage across capacitor 1, we could write, if we wanted to, as VAB, which means the voltage at point A minus the voltage at point B. Then we could say the voltage at point B minus the voltage at point C, which we call VBC. This is the voltage across capacitor 2, which is the charge on capacitor 2 divided by the capacitance of capacitor 2. This is the same value Q that we worked out before, divided by C2. So this is 96 microcoulombs divided by 20 microfarads. So that is 4.8 volts. And we notice that 9.6 volts plus 4.8 volts is larger than the 12 volts that the battery provided. But what was constant here, because the battery was not connected anymore, was the charge, since the charge has no place to go. When the battery was connected, what was constant was the battery voltage. And then to write these answers to our phys0151 three significant figure convention, this is 9.60 volts and this is 4.80 volts. If you wanted to give yourself some good self-study materials, you could imagine at least 4 different versions of this same problem. You could insert and remove the dielectric with the battery connected or with the battery disconnected. You could put the two capacitors in parallel instead of being in series. And you could also ask about the energy stored in the system under different circumstances. And you could even ask where that energy comes from. So, there might be some mechanical work associated with inserting or removing the dielectric. And if you're set up like this, where there's no battery connected, then the energy stored in the two capacitor system is changed only by the mechanical work that you do. But if the battery is connected while you insert or remove the dielectric, then you have to work out what is the energy added or subtracted from the system by the battery, and what is the mechanical work that you do, and what is the change in energy stored by this two capacitor system. So there's actually a whole range of kind of interesting problems you could make up and solve for yourself, starting from this problem.